Hello and welcome to the I2K 2022 PyImageJ workshop. My name is Curtis Rueden of the Laboratory for Optical and Computational Instrumentation, Kevin Eliceiri's lab in the University of Wisconsin-Madison. I'm going to be walking you through the Jupyter notebook that I have developed to showcase what PyImageJ can do and demonstrate some tips and tricks that you can use for doing your own science. We are going to start by accessing the tutorial. If you go to github.com/ImageJ, you will find the I2K 2022 PyImageJ workshop. You can filter here if you don't see it on top. This Git repository contains the notebook that we need and instructions on how to get set up. I will cover some of the instructions, and for the more basic things like installing Conda, you can do that on your own. I'm going to go to my terminal. You'll need to have Git installed. If you don't have Git installed, then pause the video and follow the instructions on the Git homepage to do that. We're going to make a folder for our workshop. I like to put everything in a folder called code. And then we're going to use Git to clone the repository. Git clone, paste. Inside of this repository, you should now see all of the stuff. The next step is to create our environment using Conda, so you'll need to have Conda installed. If you don't have Conda installed, then pause the video and do that first. I'm going to use a tool called Mamba, which is an alternative to Conda, but it also is Conda compatible. You can use Conda to install Mamba, and then use Mamba to set up your environments. I would highly recommend this because Mamba is much, much faster at setting up environments than Conda. So, it works just the same. Whether you're using Conda or Mamba, you'll type that, and then env create. From inside that same folder that we have cloned with Git, the I2K 2022 PyImageJ. And that will create an environment matching this environment.yaml file. And the environment will be named I2K 2022 PyImageJ. Since I've installed this before, it's already downloaded all of my dependencies at the right versions, all of my Python packages, so that step went quickly, and then it's really just about setting up the environment itself. You'll see some messages about the Jupyter extensions, and hopefully it'll complete for you as quickly as it did for me. Now, we're going to activate the environment. Conda activate. And we'll know we're in the environment because we will have Maven and Java installed. You can see that my Maven is in my I2K 2022 PyImageJ environment, and I have Java home, and it also is in that environment. So we should be good to go now. We should also have access to the Jupyter command, which will let us launch the Jupyter notebook. So now, we're going to run Jupyter notebook, and we're going to run it on our I2K notebook. This notebook will teach you to use PyImageJ from the very basics all the way through a complete segmentation workflow using both ImageJ and ImageJ2. It assumes that you know a little bit about quite a few things, but there are also links off to various other tutorials and notebooks to teach you about any areas that you might need to brush up on. And don't worry if you don't know anything, there are always links out, and I will be explaining a lot of different basics as succinctly as I can. This is a workshop focused on PyImageJ though, so that's where we'll spend most of our time, of course. The first thing that I'd like to cover before we start is these three terms, ImageJ, ImageJ2, and Fiji, which you've seen thrown around a bunch. ImageJ means the original ImageJ by Wayne Rasband. If we just say something is ImageJ, then that's what we're talking about without any context. If you see something like ImageJ update sites, that refers to the greater ecosystem of ImageJ, not just the original ImageJ application. The next term is ImageJ2, which refers to the redesign of ImageJ. Most of the ImageJ components are parts of ImageJ2, anything that goes beyond that original application. And finally there's Fiji, which is a distribution of ImageJ2 and the original ImageJ together in one application and with a bunch of extra plugins bundled. PyImageJ supports both ImageJ and ImageJ2 functionality, and you can use Fiji as well. You can use any plugins that you have installed in your ImageJ application by wrapping a local application on disk. The first step for using PyImageJ is to initialize the ImageJ2 gateway, which is a single object that gives you full access into all of the ImageJ related functionality. This gateway can be created using a function called ImageJ.init, and as our first exercise, we are going to initialize it. I'm going to link you off to the PyImageJ initialization guide so that you can fully read about all the different ways you can initialize ImageJ2 inside of Python. The way that we're going to do it is with a remote endpoint using Fiji at version 2.5.0. So that's what you want to look for in the initialization guide. So now pause the video and try to get that done. And if you are stuck or have any questions, when you unpause, I will show you how to proceed. Okay, so I'm going to click this guide, open that in a new tab, and take a look. The key section here that I'm going to jump down to is ways to initialize. And there's this handy table here which helps us understand what we need. Now we're supposed to do a Fiji at 2.5.0. So here we have with Fiji plugins a specific version, and we can see that is the incantation that we need. A nice benefit of this is it's reproducible, so this should always give the same answers forevermore as long as we use the same version of Fiji and the same version of PyImageJ. Okay, so I'm going to go here, put that in there, and I need it to be version 2.5.0, and then I can execute the cell by pressing Shift-Enter. You can also click this Run button up here, but I like the keyboard, as you can probably tell. Aha, ImageJ is not defined because you need to import it. Just try again. The first time that you run this, it may take longer than you see in this video because it is reaching out to the internet to download all of the Fiji libraries and cache them to your computer. I've already done this, so for me it was quite fast. You will also see a bunch of scary messages, as noted in this little idea bubble. These are normal and they're harmless. They're just some debug messages. There's a bug right now where debug output gets turned on when you use Fiji. But it's fine and we'll keep going. So now if we run the next cell, click in there, Shift-Enter, you can check whether it worked. You'll hopefully get a helpful message if anything went wrong, explaining what's wrong. Otherwise, if your gateway looks good, then we can continue. Part 2. We need to learn how to import Java classes into Python. One of the benefits of this approach with PyImageJ is that you can wrap any Java class into Python and use it as though it's a Python class, which gives you the full power of the Java libraries from Python. To do this, we're going to use SciJava.j import. So in the next cell, what you're going to do is import SciJava, and you're going to import the runtime class of Java so that we can do a memory check. Pause the video and get that going. So this one's pretty straightforward. You're just going to take this right here, and the only difference is we're not importing the system class, we're importing the runtime class. It's even in the same packages system, which is java.lang. Shift-Enter, no errors. Did it work? Let's try our next cell. Click in there, Shift-Enter, and it says that we have about 7 gigs of memory available to Java. That should be plenty for the purposes of this notebook. The next step is to get our data loaded into ImageJ. There are 2 ways of doing that, because we have a Python side and a Java side. You can either load your data into Java directly, or you can load it into Python and then wrap it to Java. We're going to start with the loading into Java approach. So to do that, you can use all the usual functions of the ImageJ2 gateway, including the I/O service accessible via .io. So we're going to take advantage of that to load this WT embryo sample image from the SCIFIO sample images. So let's get that downloaded. This page offers several sample images that you can use to play around with in ImageJ. For this workshop, we're going to download the WT embryo sample. And we're going to unpack it to a location of our choice. You can see all it is a single file QuickTime movie. So now that we have that data set, we can go ahead and import it using ij.io. Go ahead and pause the video and try to get that done, importing it into a new variable called embryo. We're just going to take this command and run that on wherever we saved the file. Make sure to point at the movie and not the zip file. Saving to the embryo variable. Once again, there's some debug output that can be ignored. That's okay. Let's take a look at this image and make sure that we got it imported properly. Shift-Enter. We've written a handy function here called dump_info that prints out some basic details about the image. We'll make use of this function a lot during this workshop, so make sure you get this locked down. As we can see, the WT embryo was imported. It is a default data set of unsigned byte type, meaning 8-bit unsigned data, and it's a 4-dimensional data set. The dimensional order is ImageJ-ish in that it is XY first, followed by other channels. And you can see the dimensional lengths of each of those dimensional axes. We won't cover it in this workshop, but you can also save data analogously using the save function of I/O. Let's work on getting images over to Java from Python. This is a very common use case where you'll often have a NumPy array, or perhaps an xarray, which is a NumPy array with metadata, and that you'll want to send it to Java to use with ImageJ. We are assuming that you know NumPy a little bit. If you don't, here's an excellent tutorial from W3 Schools that you can check out. We're going to start by importing a NumPy array from the scikit-image library, the cells 3D dataset. As you can see, it's a 4-dimensional dataset, and it's unsigned 16-bit, but it doesn't have any metadata about the dimensions. Fortunately, we can assign metadata by wrapping it into an xarray, so we're going to do that here. Scikit-image has some defined conventions you can read about for the order they recommend that you keep your dimensions with Python NumPy arrays. This one actually isn't in that recommended order, but it's close, and we will have some wrinkles later with that we'll deal with. Now that we have an xarray dataset, let's get that wrapped over to Java. We're going to use a function called toJava, which is part of the .py section of our ImageJ gateway. All you have to do is call ij.py.toData, pass the NumPy array or xarray that you want, and assign that to a resulting variable, and you will get a Java version of that image with no copying of pixels, so that changes made on the Java side are automatically reflected on the Python side. This is very useful for saving memory. Go ahead and pause the video and see if you can create two new variables, jcells and jxcells, which wrap cells and xcells respectively. Okay, we need jcells to wrap cells, and we need jxcells to wrap xcells. Now let's see what we can see. We have these two new guys. jcells has no metadata, and jxcells has dimensional axis metadata. They're both the same shape. The only difference is we have a data set, which is a metadata-rich image for the xarray, and we have an img, which is a very lightweight, no metadata image for the J cells. There is one other important thing that happened here. The shapes have changed. And we can see that if we compare the shapes versus how they were in Python. In Python we had plain, then channel, then row, then column, where column is X, row is Y, channel is C, plain is Z. So we have Z, C, Y, X. But here we have X, Y, C, Z, completely the reverse order. These images are still the same image. It hasn't shuffled anything around, it's just that in Java we list the fastest moving dimension first, and in Python we list the fastest moving dimension last. So in order for everything to align on each side of this fence, we have to flip it. Either way, if you iterate over the samples of an image, you will get the same order in Java and Python. It's very important that you be aware of these dimensional axis types and this order and what is what. Finally, it's worth noting that the toJava function does support other data types besides just images. This table is a quick summary of the most common types that you might want to convert back and forth between Python and Java. For every type besides images, though, it will copy the data. So if you have a large dictionary or list, expect that to be fully copied into Java and have some memory requirement there. Moving on to part 4, passing image data from Java to Python. This is all about going back the other way. So if you have data in Java and you now want to have it in Python, we have a from Java function. It's the opposite of toJava. And for the most part, it works the same as this table going the other direction, with the caveat that right now from Java does make a copy of images, will not wrap them as a view. So if you have data that originated in Java and you copy it to Python with this, it will have an additional memory requirement. If you have data that you had in Python and wrapped to Java before, there's no need to go back with from Java because you already have the original in Python, which will have the edited data. That said, for the next exercise, we are going to convert the JX cells back to Python, just to showcase one thing. So please pause the video and use the ij.py.fromJava to convert JX cells back to Python. Alright, we're going to call from Java on JX cells. It doesn't say we need to assign it to any variable in particular, just call dump info on the result. And there we go. Let's compare this against the original X cells that we had in Python before, going back and forth between Python and Java. There's one key difference here that's critical to point out. The original X cells has the following dimensional order: Z, C, Y, X. But our converted back and forth version has Z, Y, X, and C. And the reason for this is because PyImageJ makes a best effort to change the dimensional order to match with those scikit-image conventions that I mentioned earlier. So in this case, the channel dimension is preferred to go first by scikit-image standards, and therefore PyImageJ took the liberty of pushing the channel dimension to the end. This will affect the iteration order of your image. So as you go back and forth, again, make sure you're paying attention to what type is what and the order things ended up, just to make sure there are no surprises. The next section will cover slicing image data. This is not a PyImageJ specific thing. It's something that's part of NumPy, and it's a very powerful feature of NumPy. So if you're not familiar with slicing already, check out this tutorial. We're just going to highlight a little bit how slicing works with images on the Java side in particular, because we have implemented that and it does work similar to how it works with NumPy and xarray. Here's a little table cheat sheet just to show some of the most common things you might want to do. Often what you want to do is slice out a particular point of a particular dimension. So for example, if you have a 3-channel RGB image, 256 by 384, then you might want to limit it to one channel at a time. And you can do that using the colon syntax on the dimensions that you don't want to slice, and then the index of the dimension that you do want to slice. This next exercise is just going to practice doing some slicing. We're going to try slicing both Python side and Java side images, just to see how it works. So there's 4 things that we're going to slice. We're going to slice X cells twice, and we're going to slice embryo twice. And you might recall X cells is an xarray on Python, whereas embryo is a data set on the Java side. But you can slice them both. You just have to make sure that you put in the numbers in the same order of the dimensions. So pause the video and give it a try. One thing that's going to help us out here is to actually take a look again at the shape and dims of these different images. Let's start with X cells. We can see that the dimension order of X cells is plane, then channel, then row, then column. So what we know we're going to need to do is slice out the centermost plane, index 30, and the first channel, knowing that dimensions are indexed from 0, like everything in Java and Python. So the first channel will actually be index 0. And then we want to keep the entire plane, so we're not going to slice an X and Y at all. So that's what we want to do for X cells 2D. Similarly, for X cells 3D, we want to keep all the planes, the z-planes, at the second channel. So all planes, second channel, X, Y. And then for embryo, let's check that one out too. Embryo shape, embryo dims. We can see this one goes X, then Y, then channel, then time. So we know that we want to keep the XY. We want the final time point of the first channel. So the first channel would be 0. And the final time point, you can cheat and pass -1, which will be the last index. That would be for embryo 2D. For embryo 3D, again, we want the whole thing, but we want all time points of the first channel. First channel, all time points. Okay. So hopefully now this is correct and complete. Run it, and we'll check our work. Looks great. Again, if you have questions about slicing or want to learn more, check out this tutorial. Let's move on to image visualization. There are a lot of really neat ways that you can look at images in a Jupyter notebook, as well as in external viewers outside the notebook. So we'll explore 5 different ways of doing that are all useful in different situations. The first way we're going to look at is with ij.py.show, which is a built-in function of the ImageJ2 gateway for showing 2D images. It's built on top of Matplotlib's pyplot functionality, so it should look familiar. For this next exercise, we're just going to display the X cells 2D and embryo 2D images using ij.py.show. You can actually put multiple ij.py.show calls in the same notebook cell, and it will show them sequentially. So please pause the video and give it a try. Alright, this is pretty straightforward. We just do ij.py.show on X cells 2D, and we do ij.py.show on embryo 2D, and run. There we go. This function does also support passing custom color maps with the CMap parameter. And there are a lot of really neat built-in color maps to Matplotlib, which you can see by clicking on this link. So if you scroll down, you can find visual representations of these color maps and give a bunch of them a try if you want to. Many color maps. Alright, let's try with a different color map. CMap equals HSV. Quite different. Cool stuff. For our second approach, we are going to make a more dynamic visualization using the ipywidgets. This is a way of embedding some interaction into your Jupyter notebooks, and again, this isn't a PyImageJ specific thing, but I think it's so cool I really wanted to highlight it here. So first we're going to run a couple of cells just to get some functions set up. The plane function here that I've written will allow you to slice out planes of an image based on the dimensional names as opposed to doing it by dimensional index. So here you can see I've specified channel 1 time 58 of the embryo using the plane function. So now that we have that, we can actually script some sliders around it. We're going to just run this cell. I apologize for the length of it. This is not something that I would expect anyone to bang out in their own notebook. It's something that I wrote through blood, sweat, and tears, and I would like to actually have be part of PyImageJ in the future, but it isn't yet, so here it is. This is a general purpose function called ND_show, which will give you the same view as above, but with some sliders on the excess dimensions. So for the next exercise, all you have to do is pause the video and call ND_show on embryo or X cells. ND_show on embryo. And you can see that we got two sliders, one for channel, which all the channels are the same on this. That's because it is a QuickTime video that is in pseudo RGB but really grayscale. Time points, however, are quite interesting. I can use the arrow key to animate. I did say continuous update equals false by default, which is why you have to let go of the mouse every time you move a slider. If you said immediate equals true, then you can just drag the slider, but it gets a little bit laggy, so that's why the default is false. An advantage of this approach is that you can look at n-dimensional images instead of always needing to slice down to 2D. So I'm really hoping we get that into PyImageJ in the future. For our third visualization approach, we're going to look at the itkwidgets, which is a super slick way of looking at 2D and 3D data. So for this next exercise, all you have to do is import itkwidgets and use its view function on an image, and it supports, again, 2D or 3D, but not beyond that. So pause the video and give it a try. We're just going to import the itkwidgets library and call the view function on X cells 3D. We get this nifty panel here with a 3D visualization. We can control the alpha channel mapping so that you can really focus in on the data of interest and exclude all the things that you're not interested in. Here we go. The fourth option I'd like to discuss for visualization of n-dimensional data in a Jupyter Notebook is napari. It has a convenient view image function that you can import from the napari package, and you can feed it any NumPy xarray that you'd like in however many dimensions that you would like. Like the itkwidgets, napari only supports Python images, not Java images, so if you want to view a Java image, you just have to convert it back to Python first using from Java. One unfortunate thing right now is that combining napari with PyImageJ has some limitations on macOS. If you are using macOS, you'll find that this cell won't work. There is a workaround. If you click this link that's described there, if you start napari before you start PyImageJ, then you can have that viewer ready to go and you can still do this. Although I did find some problems with napari hanging. I think there is some fighting going on between Qt and Java's AWT subsystem or something under the hood. We'll try to get to the bottom of it, but right now it's a little bit dicey. The last thing you should know about is that napari can be a little finicky about the order of your dimensions. So I would like to view the cells dataset in napari, but we'll need to tweak the order to be channels, then planes, then row, then column. NumPy.moveAxis is a nice tool for doing that. In exercise 6.4, we're going to try to visualize the cells in napari. So please pause the video and give it a try. Okay, so the first step, from napari, import view image. And then we'll say view image on cells. However, as warned above, the dimension order might not be ideal for napari. Give this a try. You can see it's quite great to scroll through the different channels and the different z-planes. However, if we click this button here to go to 3D mode, it doesn't actually give us a 3D view. And that is because napari wants the z-axis before the c-axis. So let's flip them. As shown in the hint, we can import NumPy from NumPy, import move axis, and use the move axis function. So let's see, move axis, source, destination. The source can be a single dimension or a list of dimensions, same for the destination. So hopefully this will be as simple as cells tweaked equals move axis, cells, and then we need to switch which two dimensions. Dumping full cells. We need the 60 and the 2 to switch. So that's the 0th and the 1st dimensions of the shape. And now we can see that the order has changed. The channels are 2nd, and the z-planes are 1st. And if we go to 3D, we have a lovely rendering. And we can play with different color maps too. Very nice. The last option I'd like to showcase is using ImageJ itself as your viewer. If you are on Linux or Windows, you can do this from a Jupyter notebook, and I will show you how. The only catch is that you have to run the ImageJ gateway in interactive mode as opposed to the default headless mode. And unfortunately, we initialized in the default headless mode. You can check what mode you're in using this cell right here. As you can see, we're in headless mode, so I'd like to restart our notebook using interactive mode instead. A great thing about notebooks is the reproducibility. You can re-execute all your cells quite quickly. So what we're going to do is we're going to restart and clear all the outputs from what we've already done. And then we're going to change our first exercise to be interactive mode. Mode equals interactive. And finally, back down in the displaying images with ImageJ section, we are going to run all the cells again that are above where we are. And as long as you've completed all the exercises and all your cells run without error, it should run all the way down here. The star means that this cell is pending execution. There's our napari, and here we are. Now we're GUI enabled. Hooray! If you're on Mac OS, then you won't be able to use this technique. There is a Mac OS mode called mode equals GUI, but it blocks the Python interpreter. This is a technical limitation of Mac OS. So if you're on Mac, please skip to section 7 of the video. Now that we're in interactive mode, we can try out the ImageJ functions that will allow us to show images in the ImageJ user interface. The ImageJ gateway has a UI service with some functions that are useful here, including show, which shows an image, and show UI, which displays the main window of ImageJ. In the next exercise, we're going to use these functions to display JX cells in ImageJ. Please pause the video and give it a try. I would like to also have the main window available because with the main window you have access to all the commands and the full power of ImageJ. So let's do that as well. You can see here that we have our cells. We can bring up the channels tool to get a composite view. We can change the color tables. We can bring up the brightness contrast dialog, can reset that to make everything look a little bit nicer and enjoy really beautiful visualization. We can even perform interactive functions to do a segmentation in the user interface. All kinds of goodies that we can do with the original ImageJ. There's just one thing to watch out for. If you close the main window, then you crash your kernel. It will close both Java and Python. Fortunately, we can always rerun our cells again, no problem. However, just to showcase the headless support in later portions of this notebook, I'm going to switch back to headless mode before we continue. In this next section, we'll showcase how to execute SciJava scripts from PyImageJ. These are scripts that you might write in the script editor inside of Fiji itself in various languages, such as Groovy or Jython or JRuby and others. This workshop assumes that you have at least seen these SciJava scripts before. If you never have, or if you've never used ImageJ2 API, you can look at this Fundamentals of ImageJ2 notebook. You can also check out these links for information about the script framework itself and the script languages that are supported. In the following script, which is written in Groovy, we're going to compute some statistics using ImageJ Ops. So go ahead and Shift-Enter that. And then in the next exercise, we're going to execute this script on the embryo 2D image. We're going to use the function ij.py.run script. We're going to save the result to a variable called result. Pause the video and give it a try. Let's see, how does this ij.py.run script work again? It needs a language, and then it needs the script, and then it needs some arguments. The arguments are a dictionary, so that sounds doable. Run the script. Well, the language is Groovy, hint 1 says. The script we saved here, compute stats script. And finally the args we'll have to figure out. The args need to be a dictionary. Alright, so we know we need to pass embryo 2D. What's the name of the variable? The variable is called image. So we set the image to be the embryo 2D. And in case you were wondering about these other arguments, stats is an output, so we don't have to set that. Ops is a service, it will be set automatically. So we should be good to go. And here we have our result, which is a script module. That just means that it is a bag of the results, including the outputs. In this case, there's only one output, so we can grab that and check it. But I forgot to save the result to a variable. So we try one more time. Good. It looks like we were able to obtain some statistics. There is one funny thing going on here, in that the names are presented strangely. This is some kind of bug in PyImageJ, or perhaps pandas. But nonetheless, it's readable. What happened here is that we got back the statistics in a SciJava table. And then, when we call from Java on the SciJava table, we end up with a pandas data frame, which is a useful tabular data structure in Python. You might be wondering why we bothered to do these stats computation as a SciJava script. It's true that we could have just coded it in cells here as usual instead of via a script, but there are some reasons to use scripts. Firstly, if you already have a script that someone wrote, you can just call it without needing to translate it into Python. In this case it was groovy. There could be syntactic differences. Secondly, when you use run script, it runs everything in Java and then you translate the results back to Python, whereas if you have all of the lines of code separately, then there's a lot of back and forth between Java and Python under the hood, so it might be slower, depending. And lastly, this gives you the option to write scripts in various languages, not just Python. Next, I'd like to quickly highlight how to dive into the ImageJ Ops library, since it contains a lot of useful functions. If you've never used Ops before, this workshop is not an Ops tutorial, so I encourage you to check out this link, because the notebook here covers many of Ops's different functions and is quite informative and useful as a quick reference guide. At the end, there's even a list of all of the functions in Ops, including links to some dedicated documentation for some of the Ops. So in this scenario, we're going to assume that you've heard that Ops has a tubeness filter for performing edge detection, and you're interested in applying that to your data, but you're not actually sure about where this function is or how it works. So we'll start by trying to find it. You can loop over all the Ops in the system with ij.py.show, and then you can filter them. So here we see there is an op, it's called filter.tubeness. Now we can use the op.help function to see more details of how it works. Okay, so there's only one actual op implementation for this thing. We see that you can optionally give the pre-allocated output structure, you can pass an input image, you can give a single sigma, and you can pass the spatial calibrations if your data is not isotropic. So this should be enough for us to try using it, using the ij.op.run function. We've started a Python function to make this convenient. All we have to do is fill in the body of this function to call ops and return the result. So right here, we're just going to put our code. Please pause the video and give it a try. We know we need to call ij.op.run, and we know we need to pass the filter.tubeness op, and we know we need to give some arguments. There's a hint here to use ij.py.j args to wrap the ops 3 arguments. As an aside, sometimes you need to do this and sometimes you don't, just due to method signature matching between Python and Java. If you're in doubt, just go ahead and use jargs. It shouldn't hurt anything. We know we want to pass the image and the sigma and the calibration. These are the arguments of our Python function, so it's straightforward. Another benefit to jargs is that it will automatically convert this image to a Java image as needed, and so you don't have to worry about what kind of image it is so much. Finally, there's what we need to return here. We can return the result of this run call in this case, because the output pre-allocated is optional, which means that if you don't provide it, ops will generate a new output image and return that. This will take additional memory. Let's try. It looks like it worked. This is certainly a tubified version of the embryo after all, and sigma 10 looks about right. However, I would like to play with different sigmas. You can certainly do that by hand, but it's a little clunky. So let's add a slider like we did back in section 6.2, so that we have some more dynamic control here. You can see I used the continuous update this time, so as I move the slider, I just get different tubeness thicknesses. Very cool. Again, for more about ImageJ Ops, I encourage you to check that Ops notebook, which is full of goodies. You can also stay tuned for section 10.2 below, where we'll use Ops to do a full segmentation workflow. First, though, I'd like to spend some time talking about the original ImageJ API. So far we've focused on ImageJ2 features for the most part, but ImageJ, the original application and API, also contains a lot of powerful tools, and there are a lot of plugins written against this API that you might want to make use of. And so it helps to have some details on how that works with PyImageJ. While the original ImageJ API is quite convenient in many ways and simple and easier to learn, it also has some important restrictions that need to be highlighted here, especially from the context of Python. Firstly, the original ImageJ was not designed to run headless. The only way that this works is via some runtime bytecode patching that ImageJ2 does in order to add headless support to the original ImageJ application. So that is how this notebook is going to do things in the original ImageJ, but headless. Of particular note is that you still, even with this patching, cannot use the ROI Manager or the Window Manager headless, although there are some patches to Window Manager to make parts of it work, as you will see. We do make a best effort to warn you if you try to use any unsupported operations. You'll see warnings that look like this. The second thing worth highlighting is that you can only have one ImageJ enabled gateway at a time. So while it's possible with ImageJ2 to create multiple ij variables or instances, if you do that, what you'll find is that the second one does not support the legacy bridge that enables ImageJ. And you can tell the difference here based on the isLegacy active flag, is active, and also by the gateway version, which will say /inactive in the case of not having access to the original ImageJ. The first useful function for working with the ImageJ API is the toImagePlus function in ij.py. We're going to use this now to convert our xarray, x cells, into an ImagePlus named imp. Please pause the video and give it a try. Imp equals ij.py toImagePlus x cells. Now let's take a look. You can see that our X cells became a composite image, which is a kind of ImagePlus, and it has this shape. There's no T dimension, even though with the original ImageJ you always have 5D hyperstacks. PyImageJ will squeeze out anything with length 1, so that you don't have to worry about doing that yourself. When you're running in interactive mode with PyImageJ, you can use UI.show or ImagePlus.show, either one, to show the image in the ImageJ user interface. Just be aware that if you close the image window, then it might leave your ImagePlus in an unusable state afterwards, so be cautious. Finally, it's worth noting that unlike with the ImageJ2 style Java images, we have not yet implemented dtype slicing element access into ImagePlus objects yet. So if you try to actually slice them, you'll get an error saying that it's not subscriptable. This is a future direction. If you find yourself with an ImagePlus, like the result of a computation, but you want it to become a Python object or an ImageJ2 dataset, there are also functions for doing those things. So for the next exercise, we're going to take that imp, and we're going to make a dataset called imp2ds, and an xarray called imp2py. Please pause the video and get it done. Alright, let's start with imp2ds. For that one, we need to call the toDataset function. And then for the imp2py, we just need to call from Java, which will take care of making it an xarray. Now we have a dataset version with the same dimension order, and an xarray version with the normalized dimension order. One challenge when working with ImagePlus objects that isn't present for the ImageJ2 data structures is that it is possible for ImagePluses to get out of sync with their backing Python data. This is because ImagePlus makes a copy of the current plane, and then if you modify that plane, it won't be reflected in Python until you sync the data back again. Let's go through an example of this happening and how to deal with it. First, we're going to load a new image using scikit-image, and then we'll convert it to an ImagePlus. Here the variable called skin is an xarray, and the variable called skimp is the ImagePlus version of the skin. The next step will be to modify the skimp to have different data values. So there are of course many ways of doing this, but we're going to keep it simple. We're going to access the image processor object that goes along with the current plane of our ImagePlus, and we're going to call a function set with a single value that will set all the pixels of that plane to be a number of our choosing. So in this exercise, please do that with the number 17, pause the video, and give it a shot. So we have the SCIMP, and we need to get the image processor using getProcessor. And then on that, we want to call a set, and we want to pass the value 17. It looks like that worked. So let's see how things look now. So the SCIMP indeed has all 17s like we wanted, but the backing Python image still has its original values. The reason that that happened, like I said, is because we haven't synced the data back. We can do that using the ij.py.syncImage function. So to complete this exercise, we're now going to call that function. Pause the video and try it out. All we have to do is write ij.py.syncImage and say which image we want to sync, SCIMP. And then we see that in fact the skin has now got the changes, and the color has changed because we're currently on the red channel in ImagePlus land, and we just changed those all to 17s, which is close to 0, and so the red really disappears now in this image. For our next topic, we're going to talk about running ImageJ plugins. A lot of the value of the original ImageJ is in the plugins that people have written, and you can use the run plugin function of PyImageJ in order to access those, as long as they're available in your environment. If you need to access a third-party plugin, probably the easiest way to do that uniformly is to wrap a local installation of Fiji, where you have enabled the right update sites and dropped in the right plugins that you want to use. As a rule of thumb, if you can use the plugin from your Fiji installation, and then you wrap that Fiji installation, you'll also be able to use it from Python. The only caveat is that some original ImageJ plugins have hard requirements on the user interface, and so you won't be able to use them in headless mode. But you still can use them in interactive or GUI modes. The original ImageJ has an API called ij.run to allow you to run plugins, where you can pass the ImagePlus upon which you want the plugin to act. In PyImageJ, we've provided a wrapper called runPlugin, which calls ij.run, but also gives you some convenience in that the args can be a dictionary instead of the usual single string of ImageJ. So we're going to give this a try. We're going to load another new image from scikit-image, the human mitosis sample, and then we're going to wrap it to an ImagePlus. This is a single channel image. We'd like to use the Gaussian blur on this image. So in the next exercise, please use the ij.py.run plugin function, run Gaussian blur sigma 10 on the mite imp. Pause the video and try it out. So the first part is pretty straightforward in that we type ij.py.run plugin. The only question is exactly how this thing works, so let's check it out. We need to pass the plugin, followed by the arguments, and we can also pass an imp. We also need to say what style we want, but since this is the original ImageJ, we probably want that to stay true. Okay, so first the plugin, it is Gaussian blur. This is the same string you would get using the macro recorder in ImageJ and then running it from the menus or the search bar, so you can just take the same string there. Be aware that some ImageJ plugins will put a trailing space to differentiate between two plugins with similar names, so be careful that you get exactly the right string here. Okay, secondly we need the arguments, and finally we need to pass the ImagePlus. The ImagePlus will be mite imp. What about our arguments? That needs to be a dictionary. We need a sigma of 10. Sigma 10. Alright, let's give this a shot. Warning that we're in headless mode, but it did do something. Let's see if it worked. It did not, but we missed a hint. Don't forget to sync the ImagePlus after running the plugin. So, we get ij.py sync image on the mite imp. If we do that, how about now? Yes! Alright, now for the trickiest part of working with the original ImageJ from Python, running macros. There are a number of difficulties running macros, especially in headless mode, but there are ways to overcome a lot of the difficulties. The most important limitation from a Python perspective is that macros are all written to operate on an active image. So in the original ImageJ application, this is the image that has the foreground, but when we're running headless, there is no foreground, and so it's a bit tricky. That said, there are ways to activate images headless, as you'll see. In this scenario, we're going to suppose that you've received a macro from a colleague that does some operations. So this clears an image background, and then it crops down to the central portion of the image. And now we want to run this macro from Python. As a starting point, we're going to call ij.py.run macro, passing the background crop and clear macro. But we need to activate an image before we do that, or else it's unclear what we're operating on. You can do this by converting your desired image to an ImagePlus and then calling show. If you just write ij.py to ImagePlus on your image.show, then it will become the active image, even in headless mode. However, there are some problems. There's currently a bug. If you use show and you get a headless exception, this actually is because there's not at least one other registered ImagePlus already, and so there's a hack you can use to ensure that you have at least one registered ImagePlus. We're going to run a macro that does nothing else but create a tiny little image that ImageJ will then know about. I'm sorry for this step, but it is currently necessary with PyImageJ 1.2.1. We will certainly look into making improvements to the ImageJ legacy layer and or PyImageJ so that you never have to worry about doing this. So with this hack out of the way, we should be good to go on trying to run that above macro with an image from scikit-image. Let's get the coins. Now in the next exercise, we're going to convert the coins to an ImagePlus, activate it with show. Pause the video please and try. The first step is to call ij.py.toImagePlus on our coins, but there was an extra requirement here. We're supposed to title it coins. So let's save this as coins plus, and then we're going to set the title using the setTitle function. Coins, and then finally we're going to show it in order to activate it. There we go. Good. Now that it's active, we can run background clear and crop. Pause the video and give it a shot. We can bust out our friend ij.py run macro. Let's take a quick look at what this function takes. It takes the macro and some arguments. Did this macro have any arguments? It does not. It does not have any script parameters. It's just some steps. Which means we can just write run macro on background clear and crop, and that is all. Okay, it looks like it worked, but now there's a new difficulty. This macro doesn't have any outputs either. So what are we going to do? Well, we can actually grab images from the window manager, even though we're running headless. Let's take a look at what images exist in the window manager right now. There's something called coins cropped. Is that what the macro produced? If we go back up to the macro and we look, you can see that after running crop, it renames the image, the cropped image, to be whatever the title of the original was with minus cropped. So that looks promising. That looks like probably the cropped image that we want to access. So then we can say ij window manager get image on that particular one, and we can look at it. And there it is. The shape is smaller than our original image. Oh no, it's not cropped. Bugs, bugs, bugs. So it turns out that, at least with crop, when you change the ImagePlus dimensions, something is messed up in the syncing. But if we duplicate the cropped image first and then convert it back to Python, then it works. One other suspicious fact here is that I don't see a cleared background. So we might need to do some debugging to figure out what exactly that clearing background step does in that macro on this particular data set. In any case, as you can see, running macros from Python is rife with peril. So proceed with care, do your best, use the tips and tricks from this workshop, and post on the image.sc forum if you're stuck. Okay, you've made it to the final section of the workshop. There are no exercises in this section. Those are all finished. All we're going to do is demonstrate a segmentation workflow with the original ImageJ from Python, and then we're going to do it again in a very similar workflow with ImageJ2 and ImageJ Ops. We're going to use the traditional ImageJ approach, which is a 5-step approach. You can see this outlined on the segmentation page by following this link. And you can also learn more about segmenting with ImageJ from the Segmentation with ImageJ Living Workshop, which is a great set of slides that will walk you through how to do segmentation. The 5 steps we're going to follow are pre-processing, to make it easier to separate the foreground from the background with our auto threshold, followed by turning the threshold into a mask, performing morphological operations as needed to clean up the mask, finally turning the mask into some regions of interest, and finally measuring those regions of interest. I encourage you to play around with this code and try running it on different images from throughout the workshop and maybe your own data. We'll start with the original ImageJ. We'll take the X cells, and we'll turn it into an ImagePlus. We've done this before, but we're just doing a fresh one here. Next, we're going to slice out a single plane. It's easiest to work on a single plane at a time when it comes to the thresholding, and then you can always apply the same logic in a loop on multiple planes if needed, although we won't do that here. Here's our plane. It's the second channel and 36th focal plane, first time point. Note that in ImageJ original, these indices are 1 indexed as opposed to 2 indexed. These cells are a little bit spotty, so in order to make them smoother, we're going to apply a smoothing plugin. We're going to use the Kuwahara filter, which comes with Fiji. It's an edge preserving filter, so as you can see, it fills in a lot of the spottiness inside the cells. It's not perfect, but it does preserve the edges, which is important when we're measuring statistics for these cells. The next step will be to make a mask. And as you can see, the threshold didn't do a perfect job. There are some spots inside that didn't get picked up. So now we'd like to clean up this mask. We're going to use a pretty common pattern here of dilate, which grows the mask out a pixel, filling in all the holes that are left inside of structures, and finally applying ImageJ's watershed algorithm, which slices through cells that are touching but not convex. It looks like it did a pretty good job. It's not perfect. You can see here we actually closed 2 cells together and fused them, even though they weren't originally fused. That's because of the dilate. So we certainly could do a better job here, but this is a basic approach. You're welcome to try to make it better. The next step will be to convert the mask into a selection, also known as a ROI, and then saving that ROI, and then splitting that ROI. Anything that's not touching gets split into separate ROIs, which in this case is our cells. Detected 32 cells. Of course, they're not all exactly what we agree with as humans, but it's close. And finally, on each of these cell ROIs, we're going to compute some measurements. So we set what measurements we want using the ImageJ set measurements. These are the ones we've selected for this demo. And each time we run measure, we're going to get a single row added to the results table, which we're then going to harvest into a stats dictionary. You'll notice a side effect of running the measure command in headless mode is that it outputs the measurements as it goes. But the important part is that we have the stats ij dictionary now populated, and we can wrap it into a pandas data frame and visualize the output. Nifty. Once again, you can see there's this weird bug with strings iterating over characters, but good enough for now. We're going to come back to this table after we do the ImageJ2 version of the analysis, and we'll do some comparison quickly. You'll notice that we never used the ROI manager. We only used ImageJ's ROI API to split the ROIs because the ROI manager is not available in headless mode. Okay, let's move on to an ImageJ2 version of that same segmentation workflow. So once again, we're going to slice the cells. We're going to start with X cells and slice at the same spot, this time 0 indexed. There's our same slice. It's called JSlice. Now we're going to use some smoothing. This is not the Kurihara filter, because that's an ImageJ original plugin. We're going to use an op called filter.median, which is the equivalent of the median command. It's less edge preserving, although it's reasonable. That's what we ended up with. As you can see, it's slightly blurrier, so our results won't be exact. But they wouldn't be anyway, because these algorithms are slightly different. Next, we're going to apply our threshold. As you can see, it's pretty good, but there are still a couple of holes. So, we're going to do the same thing. We're going to dilate, and then we're going to fill holes to clean up our mask. And there it is. Now this next part is where it differs a little from the original ImageJ, because Ops' watershed actually returns an image labeling and doesn't just slice through and end up with a mask. You end up with a labeling. So we'll use a sigma of 10, which is configurable with Ops, and then we'll end up with an index image. We're going to display the index image with a discontinuous color table called tab 10, so that each index is a distinctly different color. As you can see here, we ended up with some blobs that are the same color, but I think that's because tab 10 only has 10 colors and that it's looping the colors. So you can see there are places where cells are touching and it's different colors. This is good. But still here, these two got fused. Finally, we'll calculate the statistics. It's going to be similar in that we're going to use Ops in a similar way to what we did back a few sections ago. We're going to call the stats Ops, including all the same ones that we used in the original ImageJ. Area, mean, min, and max, get the centroid, skewness, kurtosis. And we're going to store those into a stats dictionary, and then we're going to convert that to a pandas data frame and look at the results. Let's do a quick comparison with this compared to the other approach. So we'll go back up to that other table. Let's toss one on each side. Alright, so there's the ImageJ one, and here's the ImageJ2 one. Now, a smart person would use pandas sort column to sort by a particular column, but we are just going to eyeball it quickly. I see that row number 5 here is at x150, y18 or 19, and over here item number 6 is also at 150, 18. So the centroids are a pretty good indicator of which cell it is, especially if the areas are close. So this area of 1652 here corresponds to 1672 there. So I think these are basically the same cell. Their edges are slightly different, and as a consequence the statistics are slightly different, but we can compare them and see how well we did. So the skewness rating was 0.28 with ImageJ, 0.34 with ImageJ Ops. That's a little concerning, but more concerning is the kurtosis value. We can see that with Ops it was 3.1, with ImageJ it was 0.08. So that tells me that ImageJ2's idea of what kurtosis means is quite different than what ImageJ's idea of what it means is. Maybe one of them does a normalization, the other doesn't. I'm not sure. I leave it as an exercise to the reader. But that is it. We have done it. We've made it to the end. I just want to congratulate you on getting all the way through this workshop and learning about PyImageJ. The PyImageJ team is here for you if you have any questions on image.sc forum, or the PyImageJ issue tracker if you find any bugs. Thank you very much for your time and attention.